All right. So the meeting is now officially started. So this week, a big welcome to Daniel, who just joined our Slack group. And let's get on with our meeting with our implementations of C51. So as a matter of fact, this week, I was actually trying to make DQN work with Atari domains instead of putting too much effort into C51. The reason is that I want to make sure that I'm using the same wrappers, Atari wrappers for C51 and DQN, so that I know they're solving the same task. And the reproduction is somewhat difficult because, especially for Atari games, they have extremely large replay buffer. For example, what DeepMind uses is a replay buffer of size 1 million, and that could be very memory costly. So on commodity machine is actually very difficult. I think it actually requires something on the magnitude of 40 gigabytes, somewhere between 20 to 40 gigabytes of memory, and it's not very viable to run a lot of experiments at the same time if you're just using the same computer. But this week I mainly just try to do the experiments using DQN, try to make sure everything works. But the reproduction at the first place was very difficult, mainly because the evaluation is different, meaning that we're using a different wrapper as what DeepMind uses, and let's sort of talk a little bit about the wrapper difference. So when I was trying to do the reproduction, one of the library that I constantly was trying to look up as the reference implementation is the autonomous learning library. The reason is that they have this benchmark performance for Atari games as well as for continuous action domains, such as here. And not a lot of libraries have that actually. So even with baselines, even the better fork, the staple baselines, they don't really report something like that. They give you a zoo of the trained agents, but they don't really show you the performance. They don't really show you the training graphs of the agents in different games. So this is one of the few libraries that actually do that. So I was trying to look up implementation from there, hyperparameter choices. I want to know what they're trying to do. But then I noticed their breakout scores are very impressive, reaching about 300, 400 level. And their C51 reaches almost the perfect score. So I was mainly looking to replicate a lot of their implementation. But initially it was very difficult. I'll kind of show you an example. Let me see if I can find that. By the way, Rodson, have you got some chance to run C51 with Atari this week?
Yes, but for some reason it does not work, even on pre-punk.
Oh, really? I gotcha.
Yeah, I have no idea why.
Were you using sort of your own implementation, or was it sort of based on the what's it called
Actually, I changed my own because it was something like 10 times too slow. 10 times
okay.
slower.
I see.
Thanks for showing the way with the index add function.
Yeah. That's probably the sort of the standard implementation. But so I think this is kind of the results that I get when I was doing this initially. As you can see, the agent seems to be still learning something, but the rewards is nowhere near as good as the rewards reported by the autonomous learning library, even though this seems pretty good. But it's only getting reward of on an average about maybe 30 or so. It took quite a while for me to realize the reason why this happens was because DeepMind uses this wrapper that marks the end of life as the end of episode. However, they don't completely reset the environment. So if you look at a wrapper, by the way, sort of the source code that is going to be the base of our discussion today, I've already uploaded to the latest master branch of CleanRL, which you can find over here. There's a lot of improvement. In particular, there's no dependencies on the common module. So you should theoretically just copy and paste this code and run. It's self-contained. Um, but if you look at the code, and so first of all, this wrapper is taken from Torch Beast, which is an implementation of Impala. The reason why I use this wrapper is because it's benchmarked across a lot of Atari games, so I consider it as sort of a reliable implementation of the wrappers. Make sure I'm pretty sure they get everything right. And if you look at a wrapper implementation, there's going to be an episodic life environment where it's very important to read the description of the wrapper. It says make end of life equals to end of episode, but only reset on true game over. What that means is that in the situation, in the case of breakout, if you lose a life, it's the end of episode. However, the game is only reset after all 5 lives are lost. And that's why the performance over here is so unstable. You see constantly reaching for 0. It's because maybe at the first try for your first life, you already got a majority of the blocks bricks over here. But then at the second life, you get nothing. That's why for the second episode, you get a reward of 0, while the first life can be as good as maybe something like 400. So that was a major struggle that I had. But after realizing this issue, I sort of adjusted the way to log the reward. Instead of just printing out the episode reward, I have a real episode reward that sort of accumulates the episode reward once until the environment is truly done. And then the results makes a lot more sense. And after making sure all that sort of happens, I ran all of the experiments using try to use AWS Batch to run all of our experiments, which kind of leads to a bug, interestingly, which I'll share a little bit later. But a lot of them are still running, and then so I benchmark on the same environment that autonomous learning library is benchmarking on Beam Raider, Breakout Pawn, Puber, and Space Invader. So in particular, we can take a look at its performance. So I think this one is a Beam Rider. And to get an idea of what the rewards that we're looking for is over here. So the good one can get over almost 25,000, but maybe the medium is going to be 10,000. And is that going to be the results that we get? So for our implementation, based on DQN, we get an average reward of 7,000. And this is also an interesting visualization that I've done to visualize the QValues corresponding to each actions. And something interesting you'll realize is that for each of those gym environments, the action space is actually a little bit different, which is very interesting for me because the same spider wrapper, it's applying to all of the Atari games. So the action space should be the same, but no. So for example, Beam Rider, you have 8 actions. However, in Breakout, you only have 4 actions. So I think it can definitely be argued that action space, a lower dimensional action space, is probably going to help the agent to learn better just because you don't have to worry about too much things. But this is sort of the final rewards that was achieved by the Breakout agents. Roughly, the average is about 300 or so. And I think the best reward you could get for DQN is probably around 444 or something. I read it somewhere. Not exactly sure whether it's completely true. Um, but this is the reward, and I actually look it up, the meaning for the actions of the breakout on the right, which is kind of ironic. The actions label with 3. This is going left, and the green bar over here is going left, going right. And these two are, one of them is fire, but I can't remember what the other means. Um, but the video,
Probably do nothing.
beg your pardon,
No operation, maybe.
no variation.
Yes, like do nothing. The
Oh,
action do
no
nothing.
op. Yeah, yeah, probably, yeah. That's very likely. Um, but yeah, so you have to kind of look through these videos to find some really good performance, because even though it's even though the average is 300 or so, you do see some turbulence in the performance. Like, for example, you see a bunch of good rewards here, but sometimes you see 78, 23, and so. And because of the implementation with the monitor wrapper, we actually wasn't able to sort of record a video of the agents playing the entire game using 5 lives. So what we see in a video is actually the play of the first live, or it could be the second live, something like that. Does anyone know what this 5 means? Is this the number of lives you have?
No idea.
Yeah, because I think theoretically,
I think the 5 is the number of lives that you have. Yeah.
is a number of what?
I think it's the number of lives that you have, and it comes. It should theoretically come down
I says,
as you lose a life.
yeah, I think that makes sense. Something that doesn't quite make sense to me is that if we're only resetting the environment after the game is truly over, then one of these recordings really should have the lives being 4 or something. It shouldn't always be 5. So I am a little confused about that.
Yeah, yeah, that's true.
Yeah, that is a little strange to me. I do know, however, that I see almost perfect runs in one of these recorded videos. Huh. It almost seems earlier. So, for example, over here you see a 27 seconds run, but that is not always the case with all of the runs. And I think this one might actually. Yeah, it's very good because it gets through this tunnel over here to get a lot of scores on the top. But yeah, so this is kind of the training results for the breakout, and I think in a way you kind of have to take my word for it that if I let this keep running for 5 lives, for using all of the 5 lives, then it's actually going to sort of get every most of the bricks. And this is sort of the performance for Beam Rider. And I wonder if it shows anywhere your lives. But here is something interesting, right? Here you see the sector being different. So over here you have sector 10, but but at different time steps, you have sector 2 or something, sector 6. For some reason, it's in sector 3. So I think this is what the sort of what the episodic environment handles. That it's only reset once the environment is truly done. Something like that. I'm not exactly sure. But I think overall, it shows that the DQN implementation is quite robust to handle the majority of games. So another example is Space Invader. Um, and in particular, notice our sort of reported results is not as good as the results from the autonomous learning library. In particular, their DQN breaches on average about 350 and or almost 360, and in comparison, our results mostly resulted in something like 300 or so. But it's also it might be also important to notice that it seems that they report the score by doing the evaluation, which means no epsilon greedy isolation, but we still have the final epsilon of our setting is still 0.02, which could impact the performance. And also, in general, during the implementation of it, there's quite a bit of things that the autonomous learning library is kind of doing differently. And I'm kind of interested in knowing why they do that. So if you go to their presets, Atari DQN, what you can find is that they do things a little bit differently. So the first thing is how the neural network is set up. They actually scale the pixel inputs from 255 to a range of 0 to 1. And they also have this sort of strange linear layer that I also just kind of implemented to for the first try to replicate the results. And as you can see on the right, it basically sets the weight and biases of the last linear layer to be 0, which may or may not be important to the performance. And remember, it's kind of hard to examine the importance of each component because that would require ablation studies. But these experiments are very expensive to run. So, for example, each of these experiments are running on AWS using using a GPU instance, because with Atari games, you kind of have to use GPU instances because if you don't, it's just going to take too long and end up being even more expensive. But then you also have to select an instance that has very large memory. So right now we have 10 instances running using this instance G4 4x large. And I think that has 64 gigabytes of RAM. Yeah, 64 gigabytes of RAM and 16 CPU and 1 GPU. And I'm using the AWS Spot, so I think it's about 20 cents per hour. But overall, it's very expensive. That's why I couldn't do the ablation study. Right, this is another example, the Space Invader, and I want to check out what the autonomous learning library is able to get. So I think they get about 2,000, and mine get about 1,000 or so. But yeah, there's also a couple things that they do differently. They do some tuning. So first of all, they have this epsilon parameter in the Atom optimizer, and they also use a Hubbard loss. And lastly, for their learning rate, they also do learning rate annealing. So I think those are the three components that I didn't implement on my part. which I think in theory should elevate my implementation to the level that they achieved. So that's kind of the most of the things that I work on for this week. Does anyone have any comments or questions?
Not really a question, but regarding the memory efficiency, I do not know if you remember the dopamine repository.
Mm-hmm.
Yes, in that one they have the replay buffer does not store like the stack of 4 frames, but just a single frame, and assembles them later, stacks them later during the training. So
Could
it
you?
should reduce.
Is it somewhere dopamine GitHub?
Yes.
Could you?
Probably in the wrapped replay buffer.
Could you tell me where it is?
I'm trying to remember.
Oh,
yes.
circular.
Probably circular one. Yes. And there should be a wrapped replay buffer somewhere. Should probably search that one. It's a big file.
Okay.
Oh yes, that's the one they use.
And that could do 1 million. Did you test out their memory requirement?
That's what I'm trying to figure out. But nevertheless, compared with the current implementation, I think we should at least halve the memory cost, if not
I see.
by 4.
Yeah, that could definitely be something to implement. But I think somewhere whoever posted it in some people posted in what's called the Discord of probably the dopamine's implementation on various environment. And I don't think they perform quite well on breakout. So in particular, notice their reward sort of plateau at about 100.
But that's probably some other algorithmic reasons. But,
yeah.
The buffer, I found it quite a appealing idea in any case.
Yeah, definitely. Definitely feel free to experiment with that. See if that improved the memory requirement.
The problem is that it's heavily TensorFlow based. I think even for the pre-processing, they use some kind of TensorFlow staging.
I see.
Something like that.
Yeah, that's probably gonna take a lot of time.
I shall let you know if I get anything to work.
Okay, sounds good. But yeah, so I'm actually pretty happy with the scores that I get, even though it's not the best result that I can get over here. But I think the simplicity is important. Once you add more things, such as setting an epsilon parameter and doing learning rate annealing and using Hubbard loss, it's not exactly the same implementation anymore. It's you have a lot more tricks, I guess, and that could be important, definitely. But I think so far the results sort of matches the results reported in the paper, and overall I'm pretty happy with that. Speaking of which, what is the results reported in the paper? What was that? Yeah, in the paper, the DQN reaches about 400. So, well, I guess the paper is still pretty good, but that's also 5 million times, 50 million times that, right? We only ran for 10 million times that, which again could impact the performance, could not. I don't know. But yeah, so
a little bit. Sorry for interrupting.
No, it's fine. What were you gonna say?
A little bit of an aside, but in the end, what are the pros of the C51? Because in that on the webpage you're currently in, for example, I do not really see, aside of breakout, where like the C51 distributional DQN like seems to improve.
Well, if you look really closely, so on Breakout, C51 is performing better, and on Beam Rider, notice we're comparing with DQN, which is this gray line over here. So C51 also perform a lot better on QBirds, perform a lot better. Actually, let me make sure I get the So the light gray line. So if you notice, there are actually this gray line over here, which is a little darker, and that's A3C. So in particular, the lighter gray is DQN, which reaches about over here, right? And the categorical DQN performs a lot better. And the same thing can be said about Space Invader. The DQN is over here, and C51 is over here.
Oh, I see. So it's just a baseline problem then.
Yeah. So I think C51 still holds a lot of promises. Sort of also shown by the authors of the autonomous libraries implementation. Their C51 is usually performing better as well compared to DQN's performance. That is not always true, but
I just have a small doubt, like how, I mean, like even in C51, I was seeing the code, like instead of keeping actions, I mean, like, instead of keeping the Q values for a action, we are producing a distribution for a reaction. So what's the intuition that this increases the performance? I mean, like still we use the epsilon greedy to select the better action. So how, I mean, like, I'm not able to get the feel like why it is improving the performance.
Are you asking about the intuition as to why C51 would be an improvement?
Yes, exactly. Yeah.
I think overall it's just saying C51 is learning a distribution which could capture more information, and in a way, if you could utilize more information efficiently, then you're almost always going to perform better. Because if you have more information and you couldn't utilize it very well, then it's called a curse of dimensionality. It's actually bad for you. But I think C51, it managed to utilize more information while still remain a reasonable performance. And because of that, they just simply perform better because they're able to leverage more information.
Okay. All right.
Yeah, so that's kind of a I would say my answer to that.
Yeah, I'm getting it. Basically, you're using a distribution instead of a single Q value.
Yeah. And if you look at the link, the sort of lecture, I forgot who linked. Was it Niju or someone else who linked the lecture?
Lucas.
Lucas, as I said. Yeah, Lucas linked this video.
That if we look at the Wasserstein metric after applying the Bellman operator to two, we and you get basically.
Yeah, so over here, the professor is kind of giving an overview of the visualization of the distribution of the returns. So I think this part, if you read this lecture, I actually find it to have more intuition.
Oh, okay. Yeah, sure.
Than what's been given in the paper. Yeah.
Thank you. Thanks.
Yeah, no problem. And the reason why I did the Q-value visualization is highly inspired by that. Is that they're actually doing that, but no one really is doing that for their experiments because this is in a way more research, probably requires more setup. But my implementation on the Q-value visualization is actually really simple. It's just this much code, and that's pretty much about it. And the mechanism behind it is that the monitor wrapper of OpenAI Gym basically takes in RGB pixels and then renders them into a video. So what I do is I pass in the Q values, I generate a Q value visualization of this, and then just append the image array to the Atari games array by overriding the render methods. In particular, if it's if it's the wrapper calling the render function trying to get the image, trying to get the RGB array, I simply append this Q-value visualization to the RGB array of the game, and there it is. We see the Q-values. And so yeah, just a little project on that, and I think the end result is very cool. You can visualize a lot of things. So.
A little bit curious about the fact that all the Q values seems to be the same despite the agent learning.
Yeah.
I guess it's normal.
And another thing to notice, right? If you look at the Q values, it's actually about 60 or so, right? While the rewards is at about 1,000 level, right? And in a way, you can think of Q values. It's not exactly an estimate of all the reward that you're gonna get. So it's actually the discounted rewards, right? So that's why maybe the 1,000 shrinks to 60 because you're running through such a long horizon. But I think it's very interesting that the actual Q value is significantly lower than the episode reward that you get.
Makes sense.
Yeah. And I think Pawn is probably an example where you don't have to, analyze beyond episode because it doesn't really uses the episodic life environment, and we can take a look at its Q value representation. Yeah, so it's overall 1. And it's interesting, right? It's like as game goes on, then its values get a spike, but once the game restart, it gets to 1 again. Right. Yeah. So overall, I think this is very interesting. A very nice visualization of the decision process that undergone. And I think the same visualization can be done for actor critic agents. I think for continuous domains, it's not clear as to how you would do the visualization, but in discrete domains, we can do the same thing for actor critic agents, just basically output the probability of executing each actions.
And one question, are you using Atom Optimizer?
Yes.
I think in the original Nature DQN paper, they were using RMS prop.
Yes, that's right.
Yeah. That could be one reason for the different rewards, maybe.
Yeah, there's so many moving parts, and for example, the setting the weight and bias to 0, I don't think that's an optimization mentioned in the original paper. But at least for the current implementation, it seems to be working quite well. So there's just a lot of moving parts, and it's very difficult to do ablation study because it has such unbelievable memory requirement. But maybe Rosalind's if he gets a breakthrough with the wrapped replay buffer, that might really help us with doing Atari experiments.
Yeah.
Reinforcement learning for the poor.
Yeah, exactly.
Hopefully, necessity will be the mother of a good invention this time.
Mm-hmm.
Yeah.
But yeah,
another question regarding the Atari wrappers.
Mm-hmm.
Are you using the clip reward and wrapper?
I'm not, and I'm using the default setting of the Torch Beast environment.
Okay, I see. So there is no beating the reward to +1, 0 or -1.
No. It's implemented there, and if you want to, turn on, you can do that, but it's not turned on by default.
Then why is it there in the first place? I wonder. Maybe for the experiments, I guess.
Yeah, I would say so. We'd probably just put it there for convenience.
Good to know.
Mm-hmm. Yeah, so overall, I would say very good. And next week, I'm going to try to make the same thing with C51, trying to see if similar formats could reproduce the same results and see if C51 could produce even better results. So overall, really looking forward towards that. Let me see what else. Oh, there's also sort of an interesting bug. When I was initially running the experiments on using AWS Batch, there's actually a bug. In particular, the memory blows up. So let me see if I can find the issues that I filed in PyTorch. So we built this. So if you look at the memory requirement, it goes from 10% of a 64 gigabytes machine, and then all of a sudden it goes from about 10% utilization to 80% utilization, and eventually blows up. And that was very frustrating to debug. But then I basically roll back to using PyTorch 1.4 as the Docker image, as the base for a Docker image. And there's no such issues anymore. And you can reproduce the issue by just running this command. If you have a Docker with GPU enabled, you can just run this, and you'll be able to see exactly this. Well, technically, I guess if you use the Amazon's GPU machines, maybe they have something particular set up with them. But I think this should be a more general concept, a more general phenomenon that I hope that this bug will get resolved soon. But yeah, this is kind of what I have for this week. Don't really have any more update than that. Do you guys have any comments on what you like about the DQA, what you don't like or like about the DQA implementation? Perhaps you were hoping.
What is there not to like here, besides maybe the memory cost?
Yeah. Perhaps you were expecting to see more of the C51 implementation, but unfortunately there isn't this week. I was sort of too focused on trying to make.
Since C51 is quite based on GQN actually.
Yeah. So they share a lot. They share a lot of components, like including all of the wrappers, which are very important. So that's why I wanted to make DQN work first before sort of working on C51. But overall, I think we're on a very solid path. We have a very good benchmark implementation of DQN with sort of a cute visualization of the QValues. And we can do the same thing for C51. And after that, I hope to get A2C and PPO work on Atari as well. And at that point, I think we probably would have enough to do a major release because then our implementation would, in a way, could be considered as very high quality because it works for a variety of different domains and have good results, sort of matches the results reported by paper.
Okay. And is there any other future algorithms that you're planning for next development cycles?
I think the next development cycle is mainly tuning, right? Because so let me see. So usually for our monthly development cycle is reproduction of papers, but I think it's maybe important to take one monthly development cycle to sort of clean everything up because we have done a lot of implementation for the past year or so, half a year I would say, and there's some technical debt that's kind of piled up, and so in particular, I want the implementation of our algorithm sort of matches the reported results. So, for example, if you look at the benchmark over here, what you could see is that SAC don't match the reported results by the paper, right? So in particular, Havcheta Wait, for some reason SAC is not over here. Yeah, so for example, SAC on Humanoid, it performs really poorly.
There is actually the problem of the environment themselves.
Yeah, you could say so, but in general, it shouldn't be that bad. It should sort of match.
No, it's really different. I have tried on Mojoko and it matches the performance of the paper.
Really?
Yes.
Interesting. Okay, so yeah, that's interesting. So maybe let's look into that to make sure that we get everything right. If after examination we realize it's the environment's issue, then fine, it's not a problem. But otherwise, let's maybe investigate and try to make sure that we get everything right. Like for example, based on the implementation of the autonomous learning library, you can see that their SAC implementation on Humanoid and Walker is able to perform very well. So I just want to make sure that we have 1 monthly development cycle to sort of clean everything up to make sure that our results is actually a viable implementation, not just something that kind of works. All right. But overall, I would say we already reproduced the state-of-the-art performance on PPO, which is kind of now reflected in the benchmark right now. But I think overall we have reproduced the state-of-the-art performance by PPO and TD3. That's the two state-of-the-art results that we reproduced. And now we also have state-of-the-art performance for DQN, I'm saying. Maybe not state of the art, but it's definitely out there. It's definitely matches the reported results. So I think that's very good. And I just want to make sure the most of the implemented algorithms is going to have will similarly match the performance reported by the paper. So yeah, that's about it, about what I have. What else? Well, I also did a little refactoring. In particular, if you notice the how I use the command line arguments before, it was this. We had this discussion a long time ago, Rosalind. Remember how to deal with the Boolean arguments?
Yes, I do remember.
Yeah. But basically right now I try to use this instead, which is just convert the string to Boolean, but also use this weird thing that NRX constant true that basically enables me to be backwards compatible with all of the command line arguments that we have. That is to say, just say -- torch deterministic. Utility-wise, it's a much better implementation, but it is a little arcane. Like, for example, you don't know what NRX is, what constant equal to true means. But I think the trade-off is worth it.
As long as it works.
Yeah.
That way actually it seems more flexible, I would say.
Yeah. This gives you the ability to turn off certain features, like if CUDA is this, instead of saying no CUDA, -- no CUDA, as it was formulated by using our default, by how we handled the Boolean arguments before, now you can just say -- CUDA false or -- CUDA 0. It's very flexible.
Yes, I also happened to stumble upon some a trick that could help with reproducibility. When it comes to the GPUs, there is this function to set the seed for the GPU devices themselves. I will type in the chat.
Okay. Yeah, and if you want, feel free to just do a PR on the whole ClearL repo. But if you if you think it's maybe easier to do on my side, I'll just go ahead and do it.
I did not exactly try to see if like the random variables are
okay.
actually deterministic, but once I go down that huge to-do list I have, maybe. Sorry.
Okay. No, not a problem. Take your time. But yeah, overall, I think this is very good. And what else? Yeah, so I would say I would try to finish the C51 implementation with the Atari domains, try to see what's their performance. And in addition, there's a bunch of things that I listed on the 0.3 release. Yeah, so use a wrapper to use a gem wrapper to convert discrete action space into continuous action space by using one-hot encoding. That way, we don't have to use use anything from the common.py anymore. So then every algorithm that we have will truly be self-contained, will be single file. I think that would be a really cool thing to have because it's everything you need to know about this, how this algorithm is applied to a specific domain is right there. And it's very easy for you to customize or debugging. Yeah, and also I need to add some documentation for cloud support because sometimes, like it is the case with our DQN experiments, it's not quite possible to run a lot of the experiments at the same time using your own computer. So it's important to utilize the cloud somehow. But yeah, I think this is, I don't know, pretty much all I have. Does anyone have any questions or comments?
Great job as always.
Thanks. All right. If we don't have anything further to discuss, we should definitely call it a night early, and it's a Friday night. Hope everyone have a good weekend, and looking forward to seeing you next week. Continue with the C51 implementation. And I think last week will be our final week on C51 because I expect everything to be done at that point, and then we can start our next month of development cycle to sort of focus on the things that was mentioned in the GitHub issue to make sure the implementation is good for the existing algorithms, and make sure that we have benchmarks for Atari games, for classical control games such as Cartpole, and for continuous action domains such as PyBullet. By the way, I never got a chance to ask you, Niju, did you get a chance to do the implementation? Because I remember you were asking some questions regarding cleaner out in the Slack channel.
Yeah, I was trying to do the implementation in a Jupyter notebook.
Mm-hmm.
Yeah, because that was I'm not yet done. I'll spend some time this weekend and try to finish it up. I saw the cleaner implementation, and I'm like, yeah, they're just trying to understand things and put it in. I was more comfortable with Jupyter notebook, so I had a DQN implementation already in my notebooks, so I just trying to take this over there.
I see.
Yeah, I'm not done with the implementation yet.
Yeah. Okay, that's great.
Yeah.
Yeah, definitely looking forward to.
Let me know if in the next cycle I can contribute on things. Like.
Yeah, of course. Looking forward to having you join us to do the implementation as well, to discuss. And please let us know if you have any questions with Claro, how the library works. I think for the most part, the library should be straightforward because it's single file. There's not a lot of components. But yeah, definitely reach out to either me or Roslyn, who at this point is very familiar with the code base.
Yeah, sure. Yeah, thanks. It's so generous of you. Thank you.
Yeah. And the same thing applies to Daniel as well. If you're interested in joining us to do the implementations, definitely do, and let us know if you have any questions with using the setup that we have.
Yeah, I think I can join from the next implementation side too.
Okay, yeah, that sounds good.
Yeah.
No pressure, but
Yeah.
definitely would highly encourage you to do that, because when you do the implementation, you realize there's a lot more details, and those details are very important.
Yeah.
All right, I think this is about what I have for this week, and hope everyone have a good weekend, and see you next week.
You too. Yeah, have a great
Yeah, you
weekend.
too.
Thank you. Bye.
Yeah, thank you.
Yeah.
Bye.
Yeah, bye.